Welcome back to The Explainer. Today, we're taking a dense, challenging university exam paper and translating its intricate electrical engineering principles into a clear, visual toolkit. If you've ever looked at a complex circuit and wondered how on earth engineers make sense of the chaos, you are absolutely in the right place. This single piece of paper is completely packed with questions on Unit 2 and Unit 3 circuits, and it honestly holds the keys to understanding how electricity powers our world. We aren't just reading test questions today, we're decoding the whole shebang to extract the fundamental tools that every electrical engineer uses to master power, efficiency, and design. So here's our agenda for The Explainer. First, the art of circuit simplification. Second, demystifying the power factor. Third, the dynamics of RLC circuits. Fourth, RC circuits and power triangles. And finally, transformers and star loads. Let's get right into it. Starting with Section 1, the art of circuit simplification. Because as we know, in the real world, circuits are rarely simple. Norton's equivalent is literally the ultimate decluttering tool for an engineer's mind. The exam prompts us to find Norton's equivalent with respect to a 6-ohm load resistor. This theorem proves that any linear circuit, no matter how sprawling or chaotic, can be boiled down and represented as just one single current source running in parallel with one single resistor, relative to that specific 6-ohm load. It takes the complex and makes it totally manageable. Moving into Unit 2, we hit Section 2, demystifying the power factor. Question 4 explicitly asks us to explain the power factor and its importance. So we really have to pause here and ask, why does the power factor actually matter in real-world applications? Why is it worth 2.5 marks on a high-level exam? Well, the crucial takeaway is that the power factor acts as an efficiency rating. In AC circuits, power isn't always straightforward. The power factor tells us how much of our raw electrical supply is actually doing the heavy lifting, like spinning a motor, versus how much is just bouncing back and forth uselessly in the wires. A low power factor means you're drawing way more current than you actually need, which is horribly inefficient and super expensive. Okay, on to Section 3, dynamics of RLC circuits. This is where the math gets incredibly elegant. Question 5 sets up a classic series circuit problem, starting with a coil that has a resistance of exactly 10 ohms. Resistance directly opposes the flow of current. You can think of it like a narrow pipe restricting the flow of water. It's the foundational bottleneck in the path. But it doesn't stop there. That coil is connected in series with an inductance value of 0.14 henries. Inductors are fascinating components because they resist any changes in current. If the current tries to shift, the inductor fights back by storing energy in a temporary magnetic field, basically acting as an electrical shock absorber. To complete our trio, we add a capacitor measuring 150 microfarads to the mix. While the inductor stores energy in a magnetic field, the capacitor stores it in an electric field and actively resists changes in voltage. Now, chain all these distinct opposing components together and hook them up to a standard 200-volt, 50 Hz AC supply, you've got a seriously dynamic system. So to calculate the specific voltage across the coil and the capacitor, which is exactly what the exam demands, we follow 3 systematic steps. First, determine the total impedance, which is the combined pushback from the resistor, inductor, and capacitor at that 50 Hz frequency. Second, calculate the total current drawn from the 200-volt supply using Ohm's law. Third, multiply that total current by the individual reactances of the coil and capacitor. Boom! You've just revealed the exact voltage drops. But the real magic happens in question 6 with the concept of resonance. When analyzing the sinusoidal frequency response of a parallel RLC circuit, engineers are hunting for this exact state. It's the magical frequency where the inductive and capacitive reactances perfectly balance and cancel each other out entirely. In this state of energetic harmony, the circuit behaves purely resistively. It's absolutely crucial for tuning everything from radios to massive power grids. That brings us to Section 4, RC circuits and power triangles. Let's see how engineers turn abstract math into visual geometry. Notice how question 6 offers an or choice. You can either explain the parallel RLC circuit we just talked about, which focuses on frequency response and finding resonance, or you can analyze a series RC circuit. This highlights 2 completely different theoretical approaches. Analyzing a series RC circuit is all about mapping geometry using voltage, impedance, and power triangles to understand phase shifts. To truly understand the series RC circuit requested, we use a power triangle to geometrically map out the relationship between 3 types of power. Active power is your useful output, the actual work getting done. Reactive power is the energy just oscillating back and forth to maintain electric and magnetic fields. And complex power is the vector sum of both, representing the total power supplied. It proves that AC power isn't just a single number on a meter, it is a multidimensional relationship. Finally, we reach Unit 3 for Section 5, Transformers and Star Loads. We're zooming way out here. Question 7 requires us to draw the equivalent circuit of a one-phase transformer, but with a highly clever mathematical trick, shifting the primary parameters over to the secondary side. Instead of dealing with two separate coils linked by a magnetic field, engineers mathematically shift the resistance and reactance of the primary coil over to the secondary. This unifies the voltage, current, and impedance into one continuous, electrically connected circuit. It creates a simplified model of complex magnetic coupling that makes calculations incredibly fast. Our final exam problem looks at balanced star-connected loads. In three-phase power systems, which is how commercial power is actually generated, a star connection is foundational. We need to deduce an expression relating the overarching line voltages to the individual phase voltages. Because the three power phases are perfectly offset by 120 degrees, the line voltage mathematically proves to be exactly the square root of 3 times the phase voltage. It's a brilliant piece of engineering logic. As we wrap up this explainer, consider this final thought. We've spent our time looking at Norton's equivalence, resonance, and power triangles on a single piece of paper. But how do these exact same textbook equations and star-connected loads scale up to manage the massive, chaotic electrical grids lighting up entire cities outside your window right now? The principles on this exam are the exact same principles powering your modern life. Keep that in mind the next time you flip a switch. Thanks for joining me, and I'll catch you in the next explainer.